Hello, my name is Joshua Tyler, and today I'm going to be going over the calculation of the perimeter of an ellipse. I saw a video on YouTube. Let me see if I can pull that up just to give the proper credit where it is due. Matt Parker with Stand Up Maths, he did an approximation for an ellipse based on the idea presented by Ramanujan, who did an approximation for an ellipse. So I will be doing my take on finding the exact value of the perimeter of an ellipse. So first of all, an ellipse is a subset of a circle. Circles are ellipses, but not all ellipses are circles, where you have some x distance a and some b distance, well, some y distance b. And then the way that I decided to approach it is look at an ellipse as a unit circle. So keep in mind your unit circle is a circle around the real and imaginary components of where real equals 1, 0. This is 0, 1. And you have a circle going around here. Something like, oh, something much better looking than that. So let me undo that. Let's see here. Something like this. Something like this, where you can actually, where here let's say that this point is, well, let's say A equals 1, B equals 1. And if A equals 1 and B equals 1, the circumference or the perimeter equals 2 pi. So then if we, and this is something that you can try in MATLAB, and I may show it later, where if you plot t equals some array from 0 to 1, and then you plug in the equation e to the negative j t, or j times 2 pi t, you should get something like cosine 2 pi t plus j sine 2 pi t. And then if you plot the real of that by the imaginary component, you get the unit circle. So by knowing that, we can get we can actually plot an ellipse based on that. So if you call, and you can write it a different way by saying a times cosine of 2 pi t plus j times b sine 2 pi t. And then you can actually weight your ellipse based on an a and a b value, where b is the offset in the y direction and a is your offset in the x direction. So with that, we can write, let's say, we have a mathematical way to represent this equation. So if we do, if we zoom up on a circle, if we zoom up on it, we can, well, let's say that we have any function. Let's say for this case, we have y equals x. If we take 2 points of here, let's say that this is 0, 0, and let's say that this is 1, 1. And, well, let's say this is 1 and this is 1. We can calculate the change in x over change in y by saying we take 1 minus 1, or x of nu, or let's say we have h equals 1. That's our step size. H equals 1. Then we have x of h minus h of, or minus x of h minus 1. Geez, one note is difficult. H x of h minus 1 over y of h minus y of h minus 1. Typically, this should be, um, this bottom should also equal h, but in some cases, it may not be, where y is exponentially increasing or logarithmically increasing and x is logarithmically increasing. And this is more from a computer science point of view, from a numerical analysis point of view. This is a more exact way to represent it. But typically, it would be um, x of h minus x of h minus 1 over h, where here it would be 1 minus 0 over 1 minus 0. So dx over dy equals 1. So the same idea you can go ahead and apply. And this is exactly what I mean by saying y of h and y of h minus 0. So then if you look at a circle, you can somewhat do a rectangular approximation of it by using a sufficiently small h, where h is something like 1 times 10 to the negative 3 or something. This is how you would put it into the computer, where you would have small step size. But anyway, let's see, h equals 1 minus 10 to the 3. So then if you look at a total, um, if you look at it a different way, if you look at it using Pythagorean's theorem, where if you have some change, so let's say x and y are changing at two different values. So let's say that you have some approximation where you're checking your values here and here, where this is x and this is y. You would do you would actually do, instead of doing dx over dy, you would do Pythagorean's theorem. And remember, c squared equals a squared plus b squared. You can actually find this distance here by doing dx squared plus dy squared and do the square root of that. And that would be this change here. So you have some dx here and some dy here. So this is dx here, and this is dy here. So you would find the distance there, and then what you would do is you would cut the circle up into all of these different parts, and then once you find all the little differences, you would sum them all together. So for you would do sum uh, dx squared plus dy squared. That should equal your perimeter. Um, Now let's say h is a function of, well, let's say x is a function of t, where x f of x equals a times cosine times 2 pi times t. And let's call f of y b times sine of 2 pi t. So now, we can actually start getting somewhere, where we can find d f of x over dt should equal 2 pi times a cosine 2 pi t times dt, and then df of y over dt should equal 2 pi, or this should be negative a sine, and then this would be 2 pi b cosine 2 pi times t dt. Actually, df of y over dt. Okay, so then if we want to get dx by itself, we just multiply out by dt. So if we want to get dx, we get negative 2 pi a sine 2 pi t dt. Then dy equals 2 pi times b times cosine of 2 pi t dt. Now we can get somewhere. Now keep them. So if we square this would be 4 pi a squared sine squared 2 pi t dt squared, and then this would be 4 pi b squared cosine squared 2 pi t dt squared, and then you take the square root of all of that, and then you would do and if you see the common values, 4 pi dt squared, so you can pull all of that out of the square root by and then say a squared sine squared times 2 pi t plus b squared cosine squared 2 pi t, and then I'm going to put the 2 pi in front and say dt outside of this. So then if we want to integrate, we actually integrate 2 pi times integral 0 to 1 of square root a squared sine squared 2 pi t plus b squared cosine squared 2 pi t dt. And this makes sense because remember, sine squared of some frequency times t plus cosine squared some frequency times t equals um, equals 1. So then if a and b are the same, a and b are weighting each of them the same, so this value will be whatever a or b is times 2 pi. So if a and b are 1, then out of this function we get, well, it simplifies greatly, where we get 0 to 1 square root 1 dt, which equals 2 2 pi 2 pi what is that? That's t from 0 to 1, which equals 2 pi. So this equation, if you integrate, and let me see if Wolfram has a final form for that. Wolfram, square root a squared times sine squared 2 times pi times t plus b squared times cosine of squared 2 times pi times t. And you integrate that from 0 to 1. Let's see if Wolfram can get it. Because I'm not a mathematician, I'm an engineer, so I just tell the computer to do it. Standard time exceeded. Okay, well, lovely. Computers hate sinusoids. Okay. So anyway, so this is pretty much how you get it. If some mathematician wants to email me what this integration is, that would be absolutely amazing. but that is not mine. I'm not going to attempt that. Okay, so if you integrate that, you should get an almost exact solution. It should be dead on the money. It should be closer than any kind of approximate form. The issue with that, well, the issue with that is one, how the computer stores pi, and then two, will, um, how the computer calculates a sinusoid. So knowing that, so here, let's just plot first with a and 1. Okay, so let's say we have a ratio of 1. Ratio of 1, you see we have 1, 1. Where we say our function of t is a times cosine of 2 times pi times t plus b times j sine 2 times pi times t. Then we plot the real of that function by the imaginary component, and that's how we get this function, this plot here. And then we say dx times dt. Right. Okay, so then we say dx is the so we have dx over dt. We have dy over dt. And then we set up the integrand, saying square root of dx times dy, and then so we plot that we can plot the integrand to see what we're actually integrating. So if we plot that integrand for a and b being equal for a ratio of 1, this is what it looks like. It's pretty close to 2 pi, pretty close to 1 if we see the difference there. It's pretty dead on the money. It'll be the same. So that's what happens when you get a and b being the same. And then, so we sum times the difference, sum the integrand by the difference there, and then our error we know is 2 as 2 pi minus the difference over 2 pi, and multiply that by 100. Then then we plot, what am I plotting there? Oh yeah, dx and dy. So we have that distance here is 2 pi, and our error is 1.6 times 10 to the negative 7, which is actually, in terms of numerical analysis, that's a really low error, or well, let's say that's an acceptable error. I don't know, like when it comes to angles and sending things to Mars, maybe you want a lower error, but you also use millions of dollars worth of compute equipment there. Let's see, wait, or am I on time? Okay. So anyway, and then if we actually change the ratio to, let's say, 2, where b is 2 times that, if we look at, let's see, this is the integrand function here, and then this would be, let's see, that is dx and dy. So that makes sense that our dx is a negative sinusoid, and then our dy is a positive cosine. Positive cosine with what? It should be 2 pi times what? 2? 2 pi times 2? Yep. As close to that. Then a max value here. 6 6.2. Yeah, that's about 2 pi. And I think if you take the maximum of the integrand and find the r, so you have a peak to peak value. So I think it's the peak to peak value divided by 2 divided by square root of 2. So what is that? Square root of 2 times the peak to peak, which is the RMS value. So max of integrand times square root divided by square root 2, 8.8. It's a close approximation, I think. Yeah. it's close to that, but it's not exactly. But this shows that at least for one, at least for a ratio to one, the math follows through. So now I want to show. Let's see. I'm going to compare mine with Ramanujan's method, and this was shown in the Stand Up Maths video. I'll probably link to it below in probably in the description for this video, where Ramanujan's calculation is pi times 3 times a plus b minus the square root of 3 times a minus b times a plus 3b. So let me go ahead and click play on that. Okay, so the orange is Ramanujan's method, and this is my method, which shows that the mathematics for it is much more exact. And I don't blame Ramanujan for this because integrating a sinusoid it's no fun. Or integrating a sinusoid squared, or a square root of two separate functions. So, um, so let's see. At a ratio of 5, my error is 1.14 times 10 to the negative 6. At a ratio of 5, is a percentage error of 0.02. So, and this is based on numbers provided by Stand Up Maths. He provided an Excel sheet. So these are the values that he said are the um, exact ellipse equations. So then I'm going to show his calculations, the Stand Up Maths, and I kind of feel bad for this. I'm going to calculate these. Okay, so we have Stand Up Maths version, Ramanujan's version, and then my version. So that's how this is the proper way. This equation here is the proper way to absolutely define the perimeter of an ellipse. Thank you. If someone wants to send me the proof for the integration of that function, that would be great. Well, let me try it in MATLAB. Sims, we have a, b, and t, and f of t equals square root a squared times cosine times 2 times pi times t squared plus, actually this is sine. This is sine a squared minus b squared times cosine of that. Then this, we want to integrate f of t from respect to t from 0 to 1. Let's see, symbolic solution. Let's see if it does. Yeah, it doesn't do it. And it may be well, it's not an open form solution. Let's see, simplify. Okay, so it's not let's see, assume a equal to 1, assume b equal to 1. Let's do a equals 1. Okay. Well, MATLAB won't show me, but I know a mathematician it, that would be smarter than me. Can solve that, and probably send it in. Probably email me. My email is in my channel information. So if you want to, you know, putting the lid on, well, putting the lid halfway on this, once you integrate this function, you're set to go. Um, you should be good to go. Okay, so that is all for today. Thank you for tuning in, and I will see you next time if I do.